Okay. All right. Thank you guys for coming. Ronan's going to be presenting EDR Evasion. Very exciting. First announcement. We got third place in Seesaw. So claps for that. Beat out Carnegie Mellon, so that's huge. And yeah, with that, hand it over to Ronan.
Okay, assuming you guys can all hear me okay?
Yeah.
All right, awesome. So the main flight for today is virtual AlecX. I'll go into that in a second. It's a very common like Windows API for malware type things. The meeting, it should be under like a AV and EDR Evasion on SIGPwny CTF. I don't have it against yet. So, okay, so I want to go over a bit, like before I get into the nitty gritty of what this is, just why this matters generally. So AV EDR Evasion is very, very important, like outside of the CTF context for more real world stuff. That's because think about all the exploits you're doing, whether it's like a buffer overflow or even social engineering, they all require a payload. And that payload is going to be sitting, preferably in memory, but sometimes even on disk on another computer. And if that payload is going to get flagged by an antivirus, not only is your exploit not going to work, but now you're going to get burned and all of your tactics are going to be revealed. And it's just generally a very bad day for whatever offense you're running. So being able to get this stuff past antivirus is absolutely essential. There's a couple like assumptions we're going to be doing for this. The main thing is that we're using an actual command and control framework. I'll go into what that is in a second. But the gist of it is that in a real world context, people are not going to be running like bin sh shells, not going to be using netcat or anything like that. It's going to be like a very advanced encrypted in-memory payload that's going to have a whole lot more capabilities than just a traditional reverse shell. So the goal that I'm going to be showing you guys today is how to get one that's highly signatured by antivirus past literally every antivirus. And you can do this in like an afternoon if you know what you're doing. So just finally, this is something that like all the actual threat actors are doing. Like I have one in here later that is like a demo from like a North Korean like hacking group, but literally every APT is doing this in some way. So the command and control framework I'm using for this is Metasploit's Meterpreter. Have you guys heard of Meterpreter before? Awesome. Yeah, so if you guys who aren't familiar, Meterpreter was very evasive. It was made in like 2004, so it's on the outdated side now. But that's actually an advantage, because if you can get an outdated payload past antivirus, you're good to go with everything. So Meterpreter is actually not evasive in a modern context. So if you can get it past everything, that means your evasion strategies are good to go. And the reason you want to use this over reverse shells is a bunch of different features. It can do automatic routing for you. It can do encrypted SOX proxies. You can steal tokens, dump hashes, just run exploits entirely in memory, and a bunch of other things that are generally very good. And it's just going to help you guys translate to any of the more modern command and control frameworks. So it's kind of similar to catching reverse shell if you're running in Metasploit, but this process can apply to everything. So if you guys are running Cal, you can follow along if you want. But this is an example of an interpreter workflow. So you'd start your handler back on your host machine. It's like a listener server. And then you would generate your shell code or payload, whatever gets detonated on the target machine. It'll give you a callback to your host. And then you can start doing all the fun stuff. So this one, I just do a very basic enumeration, grab a system token to escalate privileges, and dump the hash to everything on the machine. Like that's a very watered down example of it. But that's just generally like one of the many, many things you can do that you can't do with a normal reverse shell. So, okay, so the issue is, right, this is the default detection for Meterpreter. Pretty much every single antivirus is known as malicious immediately. And not only that, it knows enough about it to disclose your TTP. So it'll say, yes, that payload you're dropping is Metasploit, like there's no ambiguity about it. And it'll also give the IP it's calling back to and the port and all the other like environment variables like the config of the C2. So all of your information is exposed.
What is TTP?
Tactics, techniques, and procedures. So it's like basically your game plan as an attacker, right? They're the little techniques you're going to be using to actually stay under the radar and move around. And it's just generally like your playbook, right? And if the defense knows what that is, they're going to be able to go after you and figure out where else you've been. So you want to keep that under wraps as much as possible. So this is why I kind of broke up the AV and EDR evasion. So antivirus AV is obviously very common. Linux antivirus is kind of a meme. You can bypass it like extremely easily, so I'm not going to cover it here. The Windows can be a little bit more formidable, especially the default Windows Defender has actually gotten very good recently. CrowdStrike stuff is quite good as well. And it's going to be deployed by default on pretty much every Windows machine. And because like 95% of corporate networks are running Windows Active Directory, this is something to be up against all the time. So bypassing it is absolutely essential if you get code execution on any Windows system. And all AV does is it's pretty much just going to say, hey, here's a file. Is it malicious? If so, we're just going to block it, remediate it, and make sure it can't get on the machine again. It's fairly basic in that regard, and it's kind of black and white. Sometimes it'll say, hey, this is a suspicious file, but most times either blocks it or it doesn't. So antivirus evasion isn't too hard. EDR evasion, on the other hand, is much harder. So EDR stands for endpoint detection and response, and this is a complementary solution to antivirus. And this is something that helps like forensics analysts figure out what is going on in the machine. So it's going to have like an event ingester, and it'll be sending telemetry constantly, being like, hey, the user's running this shell command, they're opening this process, they're calling these APIs, maybe they're reading LSAS memory, right? So like I talked a second ago about the TTPs, this is going to tell someone what you're doing on a machine. So even if there's no malware detected, if you see someone is like running who am I, net user, net group, all this stuff, all of a sudden it's very obvious those are attacker activities, and you're going to be seen as compromised anyway. So if you want to stay undetected on a modern environment with a team of people looking at what you're doing, you need to bypass this as well. Otherwise, you're just going to get caught immediately. So antivirus has a couple different detection methods I'm going to go over, because you can kind of use these as a step-by-step plan to bypass it, right? So the first one is what's called static detection. So it basically looks at the thing you're dropping, whether it's an executable or a library like a DLL of some sort. And it says look at it as extreme binary data and say, is there anything wrong with this? Like, are there any known sequences of bad bytes? Does the MD5 hash match something that we know is bad? It's a very surface level, like quick win check to make sure you're not reusing stuff. So that's why like the interpreter payload bug got caught, because the sequences of bytes that are just known to be associated with the interpreter payload, and all of these viruses, antivirus engines have signatures to figure that out, right? So that's just based off of what the file looks like statically. Think of it like static analysis for reverse engineering. Then you have behavioral detection, and this is where things get a little bit more fun. So most antivirus engines will actually run it inside of a sandbox, and they're not very realistic, but they do get the job done. And it'll say like what's happening when you run it, right? If you open it up and it's like allocating pages of RWX memory, right, and then writing to it and calling back to remote IP, that's pretty obviously malicious, even if you don't see any malicious bytes. So it'll basically figure what your malware is doing and make that, to figure out what it's doing and stop it right there. And the final one, and this is really recent, like over the last 2 years, is heuristic detection. So basically uses AI and big data and just comes up with a score of how suspicious your file looks. I don't think it's really as obvious what these engines are doing. Most of it is static based, and they'll look at things like the import address table, which I'll explain later, and other things, what functions it's calling, and just generally come up with how suspicious does this look. And you'll see that a lot with EDR solutions. CrowdStrike Falcon had one. You can use some pretty fun stuff to get around it. It could be creative. But if you guys remember the AI pie jail challenge from one of the CTFs, it's like that, but for Windows. Okay, EDR. So EDR is much harder to get around because EDR uses API hooking. So if you guys aren't familiar with hooking, it'll basically find all the functions that you're going to be calling, like for your interacting with the kernel, and it'll place a jump instruction inside of it. So anytime you call that, it'll tell the EDR, hey, this process being called by this user is calling this function with these parameters. So you can see literally all of the Windows API functions your program is calling. And I can explain Windows API a bit later. But essentially, this is going to allow it to know exactly what your program is doing on top of everything else. So this absolutely has to go. And you can get rid of it with a couple strategies. The one I'm going to show later is just grabbing an unhooked copy from disk and just straight up overwriting it. It can get much more sophisticated than that, but you can be fully undetected using something that simple. The other one is event tracing for Windows, and there are also proprietary event listeners, but event tracing for Windows, or as we call it, ETW, is the most common because it's just built into Windows. And this basically just sends events on the system, right? So if a process is doing something kind of suspicious, like reading LSAS memory, which we do dump passwords, or running a bunch of suspicious commands, right? It'll catch that and it'll be sending this telemetry, right? So you have two whole sources of telemetry to expose what you're doing. And the final one is just process tree. It's pretty much exactly what it sounds like. If you see Microsoft Word is opening PowerShell and running PowerShell commands, that's obviously bad, and you don't even need anything more like advanced than that. Just say if Word is spawning PowerShell, like stop it immediately. That's malicious. So Okay, a couple of other defensive measures, and there are even more, these are the main ones, is the anti-malware scan interface, or it's called ANSI. This is another detection feature, and it'll grab all of your dynamically run code, like scripting languages, like JavaScript, Visual Basic, C# and PowerShell. And as you run the code, it'll scan it statically and see if it has any known bad bytes. So you will actually get blocked out of running certain PowerShell commands if it has ANSI enabled. Now you can bypass this in like literally one line. But it is something to keep in mind, because if you don't do that and you're running PowerShell in memory on your beacon and you get flagged immediately, that's probably why. But you can do the exact same thing using patch event tracing, which I'll show later, and then I'll get rid of ANSI for. The other one is PowerShell constrained language mode. Again, this one isn't going to affect you if you're operating in memory, but if you're using PowerShell at all to do this stuff, it'll really restrict what you can do with it. That's just yet another hurdle that needs to be bypassed. And finally, one of the more annoying ones is application whitelisting. This basically makes it, there's a bunch of different configurations, but the normal one is you just can't run anything that's not signed. So if you just give someone an exe, right, or if you upload it to the system, it won't let you execute it. So the good fix, like the correct way of going about it, is operate entirely in memory once you get that initial compromise. However, sometimes you will occasionally have to upload things to disk. And if you must do that, you can upload it to DLL, use something like living off the land technique, like NS build, or run DLL32. I can go into that a bit later. Okay, that is all. So that is a lot, and that is just a fraction of the things that you're working against. So as an attacker, you're going to kind of need an answer for everything, right? You're going to need a bypass for every single method of detection. And I'm going to show you guys how to bypass all of these today. It'll go really quick. I was told I was hoping to change it. I'm not allowed to drop the source code, but I do have some code snippets in here for you guys to take a look at for individual bypasses. So it's very hard because you're working against pretty much the entire defense and security industry when you're doing this, right? You're trying to bypass automated detection. You're trying to make sure people aren't knowing what's going on. Like it's very difficult. So what I was going to teach you guys how to do today is to write a loader. So a loader is a way of executing shellcode undetected. And this is very important because all the command and control frameworks are going to give you shellcode. And even the shellcode is detected, right? Turning that shellcode to an exe is going to be detected. So it's this whole song and dance to get through and be able to run it. But once you do that, you're going to be able to do things you'd never be able to do with a normal reverse shell. You'll be able to be very stealthy. So the final product, it's going to be an exe. You can turn it into a DLL. You can turn it into a shellcode in and of itself using a tool called Donut. So basically, you can just turn this into your own shellcode and use it to run any other malicious shellcode undetected if you so choose. So there are a couple things to keep in mind for this, and if you're used to writing clean code, this is going to make you cringe. But there are some things you have to do with the way like the Windows portable executable format works, and I don't want to go into that here. But a couple of them is don't use global variables, right? If you're trying to turn this into an exe that can be ran in memory or into a shellcode, the global variables is stored in a different section, so it'll just crash because it's trying to reference something that doesn't exist. You can't throw, catch, or even do anything with exceptions because if you're operating in memory, there's no exception handler, so it'll just crash. You do want your payload to be as small as possible, and the reason is for signature detection. The less bytes there are, the less it can signature. And this isn't a deal breaker, but generally the smaller the better, and you want to keep it in ideally around 30 kilobytes, but no bigger than 300, at least for your loader. And the other thing is for programming languages, you can do it in whatever you want. I would recommend either C with inline assembly or C++. If you're a wizard, you can write it in straight assembly. I am not. I think TrickBot was written primarily in assembly and a couple of other ones. I think that's very difficult. So I'm going through a C++ today because you can evade everything in about 1,000 lines of C++. So it's not too bad. So the very first step is just going to be bypassing static detection. So in this case, we're using a stateless payload, just going into that briefly. All that means is the payload is fully contained versus you can have what's called a staged payload, which is going to be a tiny shellcode that will call back to your attacker server and pull the full shellcode and then run it. Those are pretty good, but not by default. If you're doing that, you want to be writing your own stagers. So for simplicity, we'll be running a stateless one, but you could use just basic. Okay. You can write your own stagers in probably 5 additional lines of code. It's not so bad.
So with the staged code, would that be flagged by any of the calls, the external calls? Didn't you say earlier that if you do have external calls to different IP addresses, you can be hacked? Or you could like. give
Yeah,
them
so we're gonna get around that a bit later. So this is something I didn't want to go into for this talk, but in order to get around that, you have to use something called malleable C2. This was the idea that Cobalt Strike was built on and pretty much everything since then. That's something that the interpreter doesn't allow. So in malleable C2, you can define all of the patterns. So you can, for example, use Wireshark and figure out what are the HTTP headers for Amazon.com and just copy that one-to-one and go into the radar. Metasploit does not allow this, which is why it's good to learn, because you're really hindering yourself by using it. But yes, you can actually do that, and there are YAR rules to catch Metasploit based off of what it does over the wire, even encrypted, which is kind of wild. So for static detection, what you're gonna have to do is, if bytes are flagged, just encrypt them. It's not that complicated. However, one thing that's not immediately obvious is because we're doing this for obfuscation and not for real security, you don't want to use something that's going to be visible as encryption, right? Because if you're an antivirus engine and you see a suspicious file from the internet that's encrypting files, most of these engines are going to be call that ransomware, even though it isn't, because it'll see it's using some kind of encryption algorithm. And if you use a library to do this, it'll actually look at what's being imported, and it can tell externally if your program is using like AES or RSA or whatever. So that's why I was going with XOR, but you can use anything you want. Like it's just total security through obscurities. In this one, I did hex and then an XOR key. You can do AES if you roll it yourself. I think that's kind of painful, but it is an option. And that's all you need to do to bypass static detection is you just take the shellcode you're going to be running and you encrypt it, and you're just going to decrypt it later. So this is an example, right? And it's kind of embarrassing how well this works considering how simple it is. I just have the shellcode as an encrypted hex stream, and once I pass a bunch of other checks, I'll show you guys later, all I do is I turn it from hex to a byte array and XOR it with the key a bunch of times, and that's it. And that's all you need to do to bypass static detection. So it's not too bad. Again, if you guys want like a specific code example, I can give it later, but it's just the general gist of it. So now we have our shellcode bypassing static detection, and we need a way to execute it. And this is a little bit tricky. So because the APIs that you use to execute shellcode are all going to be flagged, like even for importing them. So you can think of it kind of like a Windows jail, because you're trying to get to this end goal with the very creative sequence of API calls, and it's on a blacklist. So there are certain sequences like virtual alloc, write process memory, create remote thread, that'll get caught immediately. But you can get around this by using some more unknown sequences. So one of them that was used by, I believe, North Korean APT is it had the shellcode as a series of UUIDs, and then it used a function call that would decrypt UUIDs into a byte array on the heap, right? And then it used another function call that would just point to something on the heap. So if you think of it like Pwn, right? If you guys are here for Pwn, in that you have to write memory and then point to it. And that's kind of what you're doing here. You're finding a creative way to write memory and then a creative way to get that executed. So the standard one that we gave before is like the virtual alloc X sequence. That'll get flagged by everything. And the way we're going to get around this is we're just going to use the bad stuff anyway, and we're going to do what's called unhooked indirect system calls. So what it's going to do later on is we're going to remove all of the antivirus EDR hooks in a specific DLL. And then we're just going to we're going to link those functions at runtime, not at compile time. That way it doesn't get in the import address table. And then you're just going to call it directly with the function pointer in memory. So I'll go over a very specific example for that later, but that's how we're going to bypass, that's where we're executing the shellcode and bypass heuristic detection. Okay, so real quick, I figured I'd get into this because, can I see show of hands, how many of you guys have ever used the Windows API before? Wow, you guys are lucky. So the Windows API is terrible, horrible, no good, very bad, because it lets you do a lot of like the functions you'd have in C without C, which is cool, but you're kind of forced to use it, and you have to dig through like enormous documentation, right? And it's kind of unintuitive. So let's say I want to make a call to open process, right? Yeah, open process. So that'll allow me to get a handle to a process running, right? Interact with it. So to do that, I have to grab it from the kernel32.dll, which will be sitting in my process memory, right? And then when I call that function, you would think if Windows was good, it would just call it in kernel32. But what instead it does is it proxies it to kernel base, and the kernel base proxies it to NTDLL. And this is very interesting because it turns out almost all of the Windows API calls are going to be proxied to an undocumented call in NTDLL. And this helps us because if you have hooks in kernel32 and kernel base and NTDLL, well, instead of having to figure out the whole like chain for all of this, you can just unhook NTDLL and call the NTDLL function directly. And that's going to allow you to bypass all those other levels of hooks. Now, the downside is NTDLL stuff is undocumented, and it's quite a pain to work with. That's the way that the Windows OS is talking to the kernel. So it is worth knowing, and that's something that's basically required for the highest levels of stealth. So yeah, basically, instead of doing our open process call in this case and having it proxied, we'd figure out how to call NT open process and call that instead. So we're skipping steps.
So is NTDLL not like hooked?
NTDLL is hooked, but what we're gonna have to do is we're gonna unhook only NTDLL. Otherwise, we have to unhook user 32, kernel 32, and everything that goes up all those chains. All right, so this is an example of using syscalls like for NTDLL to execute shellcode, right? And this is like pretty direct. So this, if you're paying attention to the APIs, this is actually the bad chain I talked about earlier with virtual AlecX, write process memory, create remote thread. That's what that turns into, right? But now we have it all in one place. So if we unhook this, we can do all of those bad function calls undetected and only have to do it in one place. And so we can unhook user, kernel 32, kernel base, and all these other DLLs. And I have a little explanation, you guys can review it later, of what these are doing. But essentially, you're just allocating memory, putting something in there, and not pointing to it to gain execution. And this is going to get caught on its own, which is why you have to pair it with other bypasses. And I'll show that in a second. Okay. So before we can even get to the bypass part, this is the bypass in and of itself, is you're linking the functions at runtime. And this is because if you link them at compile time, it'll add an import address table of your portable executable file, all the functions that it can call, right? So if you open an executable file and you see it has a bunch of these bad functions in it, like virtual AlecX, write process memory, create remote thread, you can be like, hey, that looks pretty suspicious, even though I can't prove anything. So in order to get around that, what we're going to be doing is we're going to be creating functions like delegates, I don't know what the term is, structs, prototypes, whatever you're going to call it, as like objects, beginning of a program. And then we're going to find the function pointers to NTDLL in memory, and then we're going to call that function pointer using the delegate to basically figure out where it is at runtime. So it's not going to show up in the import address table. Now the issue is this technique is flagged if you do it the way most people do it, which is use the Windows APIs, get proc address, and then get module handle, which I'll show you an example of that in a second. But the advantage is, because Windows is written in C, you can just look at the source code of the kernel and write your own, and it won't get hooked because it's its own function. And you can combine this with another technique I'll go over later, which is called API hashing, which is pretty much, instead of calling the function directly, you'll iterate through the entire NTDLL for all of its exported functions, map that to a hash, and then you'll see, hey, which of those hashes matches the function I want to call. So that's like an antivirus engineering measure. But I promise in a second here, I'll show you the full chain, how this links together, but it does have to be kind of disjointed at the moment because of how much is going on. Okay, so this is an example of getting your code execution at runtime, right? So this is just one of the syscalls you'd use, but this is NT-allocate virtual memory, right? So you would have your function prototype for NT-allocate virtual memory, and then you're going to use get proc address, get module handle to the NTDLL, and the function name, and then it'll grab your function pointer, right? And then you can call it. So that's like the kind of high-level flow. So if you guys have any questions for how that works, I know it's all quite abstract at this point. All right. Hopefully.
So why can't you just write your own C code that does exactly what NTDLL does? Is that source just not available, or like?
Because you're going to be talking to other processes. So I don't want to go over it in this one. Like in this one, for it to be simple, it's going to be injecting into itself. What NTDLL lets you do is you can actually inject into other processes. So you can grab a handle to a remote process with something that your process isn't doing, right? So I can grab a handle to, let's say, the Windows Explorer, right? And I can put my malware, like shellcode, directly into that. And that's what the Windows API lets you do. But theoretically, you could truly look up React OS and re-implement all of it. But the issue is that NTDLL is different for every build, service pack, and version of Windows. And if you call the wrong thing, it's going to crash. So that's kind of why it's better to just grab it from memory. There is an example of that being done. You can look up syswhispers, and it's like that in assembly. And syswhispers is kind of unreliable, but it was really good for about 2 years.
One more. This is because EDR hooks procedure calls and not the actual like system calls.
Yeah, so what it's doing is whenever you call one of those NTDLL functions, it'll place a jump instruction to say, hey, process whatever is calling this function with these arguments. So if you unhook it, it has no method of knowing, but you are still calling it.
Right.
It's just the EDR doesn't know about it, if that makes sense. But it doesn't like truly know what's going on. It just knows what you're calling and makes inferences based off of that.
Is there EDR that uses syscalls instead of procedure calls, or is that too low level?
So these are technically syscalls in NTDLL.
Okay.
And the reason you have to link it dynamically is if you just put the syscall in your malware, it has what's called mark of the syscall, which is that no exe should have the syscall instruction in it, and it'll get flagged based off of that.
Okay.
Yeah. Okay, so this is a slightly more advanced example. And it's the same set of steps, just a little bit extra obfuscation. And this one basically uses a function called get API address, which is just rewriting that get proc address get module handle in C. And then it just does the API hashing technique. And just by making that change and rewriting those two functions, you're now able to link any function in Windows at runtime undetected. So it's not too hateful. It's like 600 lines. But there is, like, someone has done this before. You can just find the code to do this on the internet and modify it slightly. And after that, like, it's the exact same sequence. You just define your, your function delegate, you grab it dynamically, and then do the exact same function call. Okay, so just to recap where we are at this point, like, we're halfway there. We bypass static detection. We're linking functions at runtime, and we have, like, a very stealthy sequence of syscalls that we're going to do. So what we have to do now is we have to bypass the behavioral detection. We have to bypass the heuristic detection, and we have to unhook the DLL, right, to bypass all those sources of telemetry. So this is like roughly the halfway point. So to bypass behavioral detection, we're going to be doing something called sandbox detection. So this will basically, when your program runs, it'll be self-aware, and it'll know where it's executing. And it'll basically stealthily probe the environment to see, are we being executed in a sandbox, whether it's an antivirus engine or a malware analyst. If so, bail. You could have it self-delete. I just have mine pause execution because it's simple. And then for hooking, we're just going to be loading a fresh DLL, empty DLL from disk, because they only get hooked when you put them in memory. So if you load it first, let it get hooked, and then upload it from disk, now you have an unhooked version of empty DLL that's going to be perfectly stable. So that's where we bypass the hooking. For event tracing for Windows, it turns out everything in ETW comes from one function, ETW event right. Guess where it lives? NTDLL, which we're overriding. So you could basically just change one byte in it. So as soon as it called, it just returns. You literally just put /xc3, the ret instruction, and every time it gets called to provide telemetry on your program, it'll just bounce and say nothing's happening here. So now there's basically behavioral detection, unhooking, and ETW all done. And this is when you get past pretty much everything for the loader itself. So for sandbox detection, this one basically is to be creative and kind of play spot the difference between a real computer and a sandbox. So some of the kind of gimmies for this is, hey, if it has one CPU core, you're in a VM. Like, that's really easy. If you have like 2 gigabytes of RAM, unless you're hacking MacBook Airs, like, you can bail. That's going to be easy. If you have 50 gigabytes of disk space, that's probably not a real computer. If the host name is HAL9000, you're in the Windows Defender sandbox. I don't know why that's the case, but it is. So there are a couple things you can do like this. There are also some function calls that are not emulated in these sandboxes. The common ones are virtual alloc xnuma and FLS alloc. And if you call them, they just return null, which they shouldn't. So you can just check, hey, if I call this function, does it return null? If so, you can bail. And the other thing you can do is something that's just too computationally expensive, right? Because all these virus engines have to do it within like about 5 seconds usually. So if you just, calculate some primes at the start of your program, it'll be like, okay, I can't figure this out. It's taking too long. Let's just bail. So one of these on its own isn't going to work. But if you combine all of them together and do even more, like for example, checking the username, you can check what language the keyboard's running. So you can like region lock it that way. You can do stuff like that. You can even check the MAC address and say, hey, is this MAC address like a VMware virtual machine or like a VirtualBox thing, right? You can bail for that. So the limit really is your imagination, and the more creative you are, the less signature it's going to be. So do something funny. So this is an example of like a very basic one where it just checks how many CPU cores we have, and then it checks how much RAM there is. This is laughably effective because no sandbox is going to have more than 1 core or 2 gigabytes of RAM. So this will bail out everything. The issue is if you are like actually going after VMs in a CTF environment, that's really no fun because it's just going to also fail for that. So you might need a different set of checks if you're looking to legitimately target virtual machines. But if you're looking to go after like real stuff, this is totally fine. All right, unhooking NTDLL, fun part. Oh, sorry.
Would anything like checking user files get flagged?
Yes and no. So because we're doing the unhooking after the sandbox checks, because unhooking can be seen as malicious, it'll know what you're doing. So you have to do things in a way that aren't malicious. So if you're doing things like querying the registry key for the computer name, it'll note it, but that's not super unusual, but it knows what you're doing.
Sure.
So if you're touching files, you have to be very careful about it. So if you're dropping a file, for example, I guess another common sandbox attack is you'll write to a file and then read from it and see if the thing you wrote there is actually there, because it won't be in a sandbox. But if you're doing, let's say your program does that and has an encryption algorithm in it, then it'll think, hey, maybe that's ransomware. But yes, that is something you can do. And it'll be detected, but if you're just creative about it, it'll be like, hey, it's a little bit suspicious, but whatever, we can't prove anything. And it'll kind of move on.
Okay.
So unhooking NTDL, this is kind of the most important part for what we're doing, because we've moved all of our Windows API calls to NTDLL. Now, if we unhook this one central place, everything's going to be essentially invisible, at least at a function call level. So there's this website called iRedTeam. He came up with like one of the initial examples of this, I think. And you can just copy paste that C++ code if you want, but there are some adjustments you're going to need to make if you want to actually be stealthy. So what that one does is it basically is just going to unhook the NTDLL using like totally normal stuff. It'll grab the functions as intended, and you don't want to do things as intended. You don't want to link it at runtime using the technique I mentioned earlier, and you want to convert all the functions there into their NTDLL equivalents, like we've done already. So for example, that one calls virtual alloc, and you could use instead NT-allocate virtual memory and fetch that at runtime, and now all of a sudden that malicious unhooking routine is going to be not known, because even though you can track the functions that are being used, they don't know that combination is used to unhook a DLL, right? And then if you can unhook NTDLL undetected, then you can call anything undetected, if that makes sense. There is one indicator of compromise for this, and that's that it's going to generate a second image load event. So when your program loads a DLL for the first time, it'll generate an image load event. And no program should ever be loading a DLL more than once, unless like it's crashed or something. So nothing flags it as malicious, but if there's a skilled defender looking at your program and they see, hey, it's loading NTDLL twice, that's an obvious indicator of compromise. So it is better than the alternatives. Like the other alternatives would be to just grab the assembly in memory, like the actual syscall from NTDLL, and have that independent. But this is reliable, and I wasn't really getting fully undetected with this, and it's nice and simple comparatively. Okay, so we're almost to the end here, I promise. So the last thing we're going to do is patching ETW event right. This is like what's going to give another source of telemetry. So we already got rid of the functions, but this is like the things that your program is doing, right? If you're reading registry keys, dropping files to disk, running like shell commands, we don't want anyone to see any of that. And everything that comes from the current process, at least, you have full write permission over. So you can just grab the function for ETW event write inside of NTDLL, and you'll go to a certain offset of it, like right after the calling address, and you'll just put a ret instruction in there. So every time you call it, it just returns. And I'll have a code example of this in a second. But you can do a very similar bypass for the anti-malware scan interface. Requires a slightly different one, because you're going to be returning, the enum for AMC result buffer clean, which I can give an example for that later. But basically, all you're doing is you're changing the source code of the functions in memory to never return anything. And that's to help you go into the radar. Now, theoretically, it would be possible for the antiviruses to detect that it's been patched, but none of them do. So it's something we don't have to worry about for now. And you could go a whole nother level with hardware breakpoints. I don't do that, but that is like the most advanced patching technique right now, to my knowledge. Okay, so this is an example of patching ETW event right. So this is like an example of get proc address and then load library. So again, we want to code our own version of that in C or C++. And then this is virtual protects it, puts a ret instruction in there, and makes it executable again. Now this is the much better version, where it'll be just using an API hashing technique like before, and linking it at runtime, so it's a little bit harder to identify if it's calling virtual protect on it. And it just does the exact same setup as sequence of things. It would be even better to call NT-protect virtual memory, but I didn't find it to be necessary. But if it can be as stealthy as possible, that's another improvement you can make. Okay, so I know that was a lot. So I just need to recap what's going on, like step by step, because even though it's a lot going on, if you just follow this, like a kind of recipe or whatever, it'll get past a lot of things. So you're going to declare a bunch of delegates for the functions that are going to be linked at runtime. So like NT-allocate virtual memory, NT-write virtual memory, like NT-create thread X. I'll list like later on if you guys want to see it. But basically, you're going to be setting up the primitives for that. And you can look at React OS, that is the source code for the Windows OS in there, and that'll help you out a lot. And there's plenty of other projects that have done this kind of thing before. So that's where you're going to be kind of coming up with it. And if you go on the Microsoft documentation, Most of them are undocumented, but a couple of them for kernel development do actually have the function primitives there, and you can just grab them and copy paste. It's nice and easy. After that, you want to get a custom implementation written of load library, get proc address, and like get module handle. And this takes around 600 lines of code, which isn't too bad. And that's going to allow you to link any function at runtime. You're going to do a bunch of sandbox checks. The more the merrier. I would say at least 10. I think malware in the wild is usually doing 40 to 60, which is a little bit excessive because that's almost an indicator in and of itself. But basically, just do a bunch of checks, see if you're in a sandbox, and you'll fail. So that way, you're bypassing behavioral detection. At this point, you're going to be patch the event tracing for Windows using NTDLL calls, even though they're not unhooked yet. That's a stealthy that gets it.
I had a question about the sandbox checks.
Yeah.
So you had 2 examples of the CPU cores
Yep.
and the size of your RAM.
Yep.
What other sandbox checks could you have?
Yeah, so one
They-
big one that I didn't mention is they're all going to be running something called inetSIP, which is a fake internet. So you could, for example, store the key to your shell code at a server, right, and not do any at all. So one thing you could do is you could say, hey, query my server, grab the key at runtime, decrypt it, right? But if it's not getting a real result, it'll try to load a bunch of encrypted assembly and just site fault. So that's like, if you're looking to do it in one go, that's about as clean as it gets. But a couple other examples would be, you can check like what type of keyboard they're using. So you can target people by region. You can check the MAC address and see, does this have, all VMware machines, for example, have their own MAC address. You can say, hey, this VMware machine can fail based off of that. So outside of that, though, you kind of have to be creative. If you're targeting, like doing like spear phishing, you can actually check if the username of the person executing it is the name of the person you're targeting. If, let's say you're doing Active Directory and you know their naming scheme, and it's just, you can do that. So it's really whatever you can think of. There's no like clear-cut way for it. And the more wacky you can make it, also making it work, the better, because it's based off of what people have done so far. Outside of that, so after we patch ETW, you're going to unhook NTDLL. And sometimes, like, it's a little bit finicky depending on what AV and EDR, but sometimes this patch will prevent that second image load event, so you won't have any indicator of compromise, but it's a little finicky. So it really depends on the product you're running. And finally, after that, you're just going to decrypt and execute your shell code using syscalls entirely from NTDLL. So you can see you're going to be bypassing static detection because you have it encrypted. You're going to be bypassing behavioral detection because of the sandbox checks. You're going to be bypassing heuristic detection because you're linking functions at runtime. You're going to be bypassing hooking and event tracing because of the patches to NTDLL. So I do have a couple other like extra tips generally if you guys are looking at being stealthy beyond just the initial compromise. So the main one is, you don't get taught this a lot. Dropping any file directly to disk is bad because it can be recovered. You want it to live in the RAM because it's like volatile memory, and that way, once the computer shuts down, you don't have a trace. And you could do this like by taking this loader, and you can use a tool called Donut, or you can also turn it into a DLL and then turn that into shellcode. And that's why I was like before, don't use any global variables, don't use an exception handlers, because we're going to turn this into shellcode for, say, a buffer overflow exploit or something, hypothetical like that. That's how you would do it. So, sometimes, and this is venturing into the realm of the cursed, you will need a loader for your loader. If you're like phishing, for example, and you got to use Visual Basic, Visual Basic has to call these WIN APIs. So you have to write something that'll fetch the loader and then load that in memory. Same thing goes for like HTA files, or if you have to call it from like JavaScript, because you can write malicious JavaScript to do this. So that's another thing you have to worry about. And the last thing is something I don't follow myself because I'm fine rewriting this program, but don't submit it to VirusTotal or hybrid analysis. Like here, it's cool because I can have this big screen that says, hey, it's undetected. But what will happen is it'll get put into the the analysis they're doing, and it'll say, hey, this is probably a malicious file. Let's adjust our big data heuristics to detect it, right? And I actually I've had a real human being, I think, signature my malware before, because I'm entirely unstealthy. So I'll just put things like fully undetected meterpreter.exe. I'm like, yes, some dude has actually written a signature for that manually. So I did have to rewrite an old thing I did like about 4 months ago because of that. So something to keep in mind is the security community might actually see what you're doing. And you're gonna want to avoid that unless you're like me and like doing this stuff. So the other thing is, in terms of the actual payloads, I talked about Metasploit for simplicity. The good ones, Cobalt Strike is like the gold standard, but I don't have $9,000 a year to burn on it, and I don't think anyone here does. So for open source versions, Sliver and Havoc are quite good. Those are also command and control frameworks. They can do all the things that Interpreter can do and a little bit more. and they use a lot of the evasion techniques I'm talking about. So they're doing things through NTDLL. They're grabbing functions at runtime. They're doing all of the kind of evasion stuff. So that way, once you do get it in there, you're not going to be triggering EDR anymore, and you're going to be able to run everything in memory. So like those ones, for example, instead of running shell commands, they have aliases. You can run whoami, ls, whatever, entirely in memory. So no EDR is going to pick up on you doing all of those potentially malicious commands. So that's quite cool. And that's kind of how you stay undetected after this initial compromise. There are a lot more evasion techniques I didn't go over. You could do direct syscalls, sleep obfuscation, like call stack spoofing, like all sorts of different things. If you're really looking to get creative, if you are like, if for some reason you're just doing to challenge yourself, you can put an anti-debugging, anti-reverse engineering techniques. This is something that real threat actors do all the time. You can also get creative with it, like a sandbox. Like for example, if you're in a debugger, the heaps can be allocated differently. You can just check for that and make it just something really funny if you know you're being debugged, like pop a message box, like to troll them or whatever you want, or to self-delete. And the last one is, even though like this already had a lot going on, this is as easy as it gets. So if you're looking at doing it in like an interpreted language, like Visual Basic or like a JavaScript dropper or something, like it's going to be even harder. So evasion is kind of a skill because depending on how you're getting that compromise, you need to rewrite the same kind of thing in whatever language the target's running. So, all right. So that's about it for now. If you guys need, because I know this was very technical and very dense, I have the source code for this. If you guys are looking for like a concrete example, I can give that out. I can't give a demo if you're interested, but it's quite boring because literally just I execute it. It's undetected. It executes. So nothing super, crazy there. But again, if you guys are ever looking to write this kind of thing, just let me know, send me a DM on Discord, and I can help you like debug it because it can be incredibly frustrating to write this. So, and yeah, so that's the meeting flag again. And if you guys have any questions, let me know.
2,000, awesome.
It goes a little dense, but it'll do.
So, it's like, yeah, like, this is like the most advanced thing. It's like 1 line.
Yeah.
I bypass it in 1 line, so we don't have to worry about that.
Yeah. I mean, if you guys are cool with it, I can actually put the loader I used to shame CrowdStrike. I have that in like ready to go. If you guys want to see the C++ source for it, and just
That's so
copy paste.
sick.
But
that whole process sounds like so interesting, though. How did you like even learn about?
So after I finished OSCP, which was like in like July, I just figured like I want to do like more realistic stuff. So I just studied this like ever since then, like off and on. And a lot of it has been looking at like what the most advanced threat actors are doing. Like a lot of people will talk about like tradecraft from 2014, like like PowerShell downgrade attacks or like stuff, and it can get so much more advanced. And I just kind of figured it out by being my own blue team. Basically, I put an EDR on my VM. And I looked at the event logs, and every time I detonate a payload, I would just look at it and see like, how can I tell it's doing what it's doing, and then how can I bypass it? And that's how I got to the point of stacking like all this different stuff, on top of itself. And it goes like this rabbit hole goes so much deeper because this is just to execute one file. Like if you're looking to run shell commands and enumerate and do fileless lateral movement, and like dump passwords, you need to repeat this kind of process of like figuring out how does it get detected and how do I bypass that for everything. So it is kind of like a learned skill in that sense. But yeah, no, I just figured out by trying to catch myself and trying to see if I can make it invisible again.
So do you have a Windows VM then on your own?
I do, yeah. It's a little bit like
boots like a certain OS. Like which Windows operating system?
I just do Windows 10 because it's easy. What I'm gonna do later, especially if I build some challenges for this place, is you can get free Windows Enterprise using the UIUC Windows keys. So you could probably grab that and grab a free trial of CrowdStrike Falcon, and then put on App Locker and like all the application whitelisting, and then like a really locked down environment to run it on.
And then really try and like bypass.
Yeah, and then you could try and bypass it. The issue is if you're running in memory, it's so effective that none of it matters. Because all the stuff to limit your shell commands and all that aren't going to matter because they have no source of telemetry, and you're running everything entirely in memory. So like I don't know if you guys have actually taken a look at like the structure of the file, but if you're running whoami or whatever, it's not a function of like bash or cmd.exe. That's actually a file on the computer, and they can see that you're calling it. So like the more covert thing to do now is use like it's called beacon object files, which is basically a .o file from C, and you actually put that in memory of your implant and run it. So people have like rewritten the entire shell to work with that stuff.
So then with the current modern day antivirus software, how low level does it get? Like obviously you were talking about Windows Defender in this example. Does CrowdStrike Falcon like protect files that deeply, or
So
are you?
they all do the same thing. So in my opinion, from my testing, Defender and Falcon are the best. Like from what I can gather. Again, I'm not like doing cyber defense professionally, so it's just my opinion. So they do a lot of stuff. Like I said, like that was just the basics. But the reason this works so well is you're targeting what foundationally makes antivirus weak, right? Like they're not going to be scaling up, like the amount of RAM or whatever like a sandbox has. But like in terms of protection, it's already as low as it can go in that it's hooking what the kernel is doing. So like that's something that like rootkits do on the offensive side. I don't think it could possibly go any deeper. They used to do that actually, so they used to be able to load their own drivers and monitor things like a driver level. And Microsoft got rid of that because they were horribly unstable. Like the defense kind of went a couple steps backward with that. And it's kind of back now with like mini filter drivers for some EDRs. But I don't know that much about it. Like, but yeah, it's about as far as you could reasonably go. In terms of protection.
Wow, that's crazy.
So are you pretty close to like the end game for EDR evasion then? Because
So,
like it seems as if you're like quite similar to like what a process might be doing. Like it doesn't seem like that abnormal. Like the
Yep, so that's the thing, right? So my kind of philosophy for this, there's a bunch of different ones. I like to do evasion through benign functionality. So in this case, like the alternatives would be you could actually take NTDLL, right? And then grab the function primitives beforehand and put that in there. But you know, even though that's effective, that's not benign functionality. So yeah, I've taken it as similar as I can by actually grabbing things like I'm calling the syscalls from the NTDLL that I'm given, right? So it's where it should be coming from, and stuff like that. So it's as good as it gets for now. But for reference, the stuff has advanced so much in the last 2 years that I can't predict where it's going to go in the future. But from what I can gather, from what's on the open internet and from what you can find, like looking at what threat actors are doing, this is about as good as it gets in terms of evasion. Like to the point where there are actual threat groups that are using these specific techniques. So
when you say it's like developed so much over the past 2 years, what has developed?
So the big one is the heuristic big data detection. So like that wasn't even a thing a little while ago. Like it was kind of a meme, and now it's actually gotten quite good. So that's the big
references the AIML like pattern detection.
Yep. Yeah, and it's like a holistic evaluation, and you can bypass that by doing things that are just holistically really weird. So for CrowdStrike, I lowered my suspicion score from 60 to 0 by embedding the U.S. Constitution, and the reason is it holistically looks at the size and entropy of the file, and that's how it calculates suspicion. It was able to increase the size and lower the entropy by doing that. But the issue is like sandboxes were already a black box, and they're quite hard to figure out. The AIML, like, good luck. If you know what it's doing, like, please tell me, because I'm basically just guessing until it works.
Please don't tell Ronan. Whoever you tell, don't tell him. That's crazy.
So if you can bypass all this stuff using just like over 1,000 lines of code, what's kind of the difference between this like above level of a script kiddie and then a nation state attacker?
So I mean, the big thing with the nation state attacker is well, the real big thing with them is they have deals with the antivirus companies, so they will never get signature. So in terms of loaders, like this is not too dissimilar to what Stuxnet did. So that was, now obviously they're 10 years ahead of the game, but it's like a very similar thing. With nation states, they're going to be using a lot of 0 days for like impairing defenses and other stuff. So that's like the next level up in malware is combining it with like, Rev and Pwn and whatever, and doing it to like worm your way through a bunch of different computers. But in terms of evasion, like this is about as far as it goes, to my knowledge. Like I don't think you can go any deeper unless you want to like write a rootkit and hook things and be like, hey, as the kernel's iterating through the processes, if it's the one I'm running, like hide it. So that's I think the only way to go any deeper would be to write a rootkit.
What's a rootkit?
I mean, that's kind of a loaded question, but it's basically malware designed to hide your malware. And what you can do is, like when I was talking about the EDR hooks, right? One common one is, let's say, you're a game hacker, right? And you want to hide your game hack from the, anti-cheat. you can actually hook the thing that you use to iterate through processes in Windows, and like we patched that to return like patch ETW, right, to return in certain instances. You can say, hey, if the process you're iterating through matches the name of my malware, it wasn't there. It just wasn't found. So you can use it to overwrite all of these like enumeration functions in memory and make it so, hey, if you're looking at the static files where I'm located, it's empty. It's not there, right? If you're looking in the memory where I am, it's something else.
You just like reprogram the.
Yeah, it's like you're reprogramming the OS. That does require system privileges though. And you have to actually be good at writing drivers for Windows, and I'm not good at that, and I don't like to assume that I have system. So it is a little bit conditional in that regard.
Have you looked into like how you blue team this as someone who's like not writing the actual antivirus?
Yeah. So please realize like the number of people going through this much effort like to get their malware is basically just nation state actors. Like most normal days are not doing this because this is like an enormous amount of effort. The issue is, so there are tools like Mineta and PECIV, and what they do is they'll actually iterate through memory and look for places where what's on disk doesn't match what's in memory, right? So other techniques I didn't go over in this one is you'll inject into, like for real malware stuff, you're gonna be injecting into other processes. So you'll put your malware as an explorer or service host, right? And for the blue team, what they'll do is you can iterate through and check, hey, is the stuff with service host is running actually service host? And if not, you can say, hey, that's been maliciously overwritten. You can get around it. Like the issue is for every one of those detection vectors, there is a bypass. So you do have to kind of pick your poison in that regard. But it's been an issue for a long time for blue teaming what they call fileless malware, stuff that lives in memory. So the biggest thing for a blue team is even if you have no idea what's going on, you could see, hey, if this thing is, even if it's like using a statistical like exponential distribution, right, to look a little bit more random, if something is making HTTP requests to a remote endpoint like that nobody has ever heard of every 5 seconds exactly for like 4 days, that's probably a beacon. And you can get around that like by like coding and like only beacon back during like working hours and all that. But if you're going to be looking at it and you have like deep packet inspection, a human analyst would be able to see like that's probably something on this machine is beaconing out, or like it'd be more like what the actual behavior is doing. Like, hey, if you see a machine that doesn't look infected making like 500,000 LDAP queries, like to write out like Bloodhound, for example, that would be a way of blue teaming it. But in terms of like endpoint detection, there's not a lot you can do because if there was, it'd already be doing it.
That was awesome.
All right, do you guys have any other like questions?
I just want a second round of applause. That was
Yeah, such an awesome presentation.
Oh, well, thanks. And if you guys want, there was like an enormous text wall. Like I did the code snippets in there so you could copy it. But you know, admins, if you guys are okay with it, I can just put the C++ file like as an attached thing to the meeting flag, and you guys can go download and look through it if you want.
Yeah.
All right. And I'll get to that like later today. All right. Well, thanks for coming, guys.
Basically, only like terrorists do this, but